simple linear regression. Let's suppose that I own a pizza shop and I'm looking at how much I spend on advertising and the impact on my sales. So I may just want to record that. This is my advertising amount I spend on advertising, and this would be my sales. And hopefully what I'm going to see is as I spend more money on advertising, as advertising increases this way, that sales is going to also increase. So hopefully I'm going to get something that looks like that. It doesn't have to be exactly like that. It may have some sort of fluctuations in it, but it's trending upwards. So here I'm actually looking at the impact on advertising on sales. Here, sales, I would imagine, would be dependent on my advertising. So here I would call sales my dependent variable, and the dependent variable has the symbol y, and the other variable that I use to predict the dependent variable is called the independent variable and has the symbol x. So this may be quite useful to me to see if it's worthwhile doing more advertising based on my sales. If my sales are not really improving with the advertising and not improving by enough, then I may not continue with the advertising. Let's look at another example. Let's consider students that are going to take an exam, and let's suppose that the exam score is going to be recorded. So that's their exam score, and we're also going to actually record the hours they spent studying. And let's put the hours studying down here. Let's just put hours here. And what we'd like to do is actually get a bunch of students and plot their results on here, whatever it looks like. And what we'd like to see, as you spend more and more hours studying, that your exam score increases. That's what we'd expect to see. We'd expect some sort of upward trend. It may not necessarily be a straight line, but some sort of upward trend like that. So again, we've got two variables here. We've got the exam score and the hours studied, and we're seeing how they interact with each other. And one of these would be called a dependent variable, and the other one could be called an independent variable. I think it'd be quite safe to say that the dependent variable would be your exam score, because your exam score, you would imagine, does depend on how many hours you spend studying. So this again will be called the dependent variable, and it will be given the symbol y. Dependent variables are commonly given the symbol y. The independent variable, the predictor variable with the hours studied, this is going to help us predict what your exam score is going to be. The more hours you study, the higher your score. So that we're going to call that x, and that's going to be the predictor variable or the independent variable. So, and again, likewise over here, this was the dependent variable. Sales with the dependent variable, say, depending on how much you spent on advertising, how much advertising you did. So we want to get to the position where we can model it. We can take a bunch of sample data, say, of students. So this is the hours they spent studying, and this is their exam scores. And we could keep a record of it. So you study so many hours, you got this score. Another student studied this amount of hours, got this score, and so on. And then we want to model it by fitting, in this chapter that we're looking at, a straight line. And we want to find the best fit straight line through that data. So we have to figure out what is the best fit straight line to put through that data. So why we're going to fit a straight line to the data? Well, there's different reasons that we can look at for fitting a straight line to data. First of all, we have to do a couple of checks, and we're going to do an example shortly so you can see what I mean. But if the data, when you plot the data, if it kind of looks as if it could be linear, then we're actually going to try and fit a straight line to it because it's quick and easy to do. And we're going to fit what is commonly known as a simple linear regression line. Now, the actual line for this data that I've drawn here, that I've just made it up, if I was to draw a line through it, it would look something like this. Doesn't lie exactly on a straight line at all. And that red line, if I was to actually tell you the equation of the red line, it may well be something like this. Y is equal to beta 0 plus beta 1 x, which is, most of you will be familiar that this is the equation of a straight line. But the red line is not a straight line, and we're going to add in this e error, or epsilon, is the Greek letter E, which basically is the error. So we're saying the red line, it could have been a straight line, but it's not exactly a straight line. It deviates from the straight line by this error term, and that error term is going to be the difference between the our estimated line, if the purple line's our estimated line, and the reality, the black points are the reality of what actually happened. So right here, the error term, I'll do it in green. So the error term we'll do in green. So we'll say the error term at this point is this amount here, because that's how much deviation we have from our estimated line and the actual what actually happened. Here it's going to be this much, here it's going to be this much, here it's going to be this much, and here it's spot on. So this E, or error, or epsilon is the difference between what you estimate, which in this case would be the purple line, and the actual data, which are the black points that I actually put over on the point over here. There's another word which is called residual, and a residual is similar to the error term. A residual is when you're dealing with sample data, and the error term is when you're dealing with population data. So right here we're actually dealing with population data, and what is this in here? It's the intercept of the population, and this guy in here is the slope of the population.